Hello grade 11 and grade 12 learners. In this video, we're going to be going over the grade 10 electricity, electric circuits topic, and it's very, very important that you watch this video and you go over the grade 10 stuff first, because in grade 11 and in grade 12, you use the concepts and everything that you learned in grade 10 again. So let's go. Understanding series versus parallel circuits and what happens to current and what happens to voltage within these circuits is very, very important. So on the screen, you can see a summary of that. And the two most important things to remember is that in a series circuit, current is the same everywhere throughout the circuit, but voltage splits. In parallel, the opposite is true. So the current splits and voltage is the same for resistors connected in parallel. So if we compare these two circuits over here, let's look at the series circuit first. What it means is, do you see that the ammeter over here measures 1.5 amperes? Now, remember we said in series, current is the same everywhere in the circuit. What that means is the total current is 1.5 amperes. So 1.5 amperes will flow through the battery. 1.5 amperes will flow through the ammeter. 1.5 amperes will flow through the 2 ohm resistor. The reading on A2, the reading on this ammeter is 1.5 amperes. 1.5 amperes flows through the 4 ohm resistor. 1.5 amperes flows through here and back to the battery. There are no splits in this circuit. There are no resistors connected in parallel. So current is the same throughout. So that is what it means by current is the same. However, voltage splits. So what that means, and I really, really want you to understand this carefully. What that means is the voltage across the battery. You can see here it says 9 volts. So what that means is if I had to connect a voltmeter across the battery like this, remember, voltmeter reads potential difference or voltage. If I had to connect a voltmeter across that battery, it would read 9 volts. Now that 9 volts is the total voltage, total potential difference, or external or terminal potential difference. Okay, terminal potential difference. And that 9 volts is split amongst the different resistors or components in series. So some of the 9 volts will go here and the rest will go here. We can actually work out how much voltage will go to this resistor. I hope you remember the formula. V is equal to I times R. Remember, I is current, the total current, the total current flows through this resistor. So 1.5 amperes. 1.5 amperes flows through that resistor, and the resistance is 2 ohms. So that means that the voltage V1 is 3 volts. So what that means is that when V1 has a reading, V1 will read 3 volts. If I had to do a similar calculation, but for this resistor over here, it will be V equals I times R. Current, once more, is 1.5. Remember, the total current, 1.5, flows through both of these resistors, times the resistance over here is 4. And 1.5 times 4 is 6 volts. So this voltmeter over here will read 6 volts. And I hope you can already see what's happening. If I take 3 volts plus 6 volts, it gives me 9 volts. And that just shows me that voltage in series is split. Just what it says there. So of the 9 volts across the battery, 3 volts goes here, 6 volts goes here, 3 plus 6 is 9 volts. Let's look at the parallel circuit. Parallel circuit is the opposite. Current splits in the parallel circuit. So what that means is if we look at the parallel circuit, the total current will flow here because these parts are in series. The split has not happened yet. So this would be total current. Total current. As soon as you get to a split, as you can see here, the circuit line splits. As soon as you get here, if you go this way, the circuit line splits. Some of the current goes through here, as I've mentioned previously in this video, and some of the current goes through here. So current splits in parallel. Current splits. However, voltage is the same. And what that means is if you take a look at the circuit, we have no resistors connected in series here. We have the 1.5 ohms and this 1.5 ohms connected in parallel. And what that means is the voltage across this 1.5 ohms is the same as the voltage across this 1.5 ohms. And in this case, those voltages will be the same as the voltage across the battery because they're all in parallel. So the battery, if I had to attach a voltmeter across the battery, it would read 9 volts because it says 9 volts over there. That means that V2 would read 9 volts. That means that V1 would read 9 volts. That is because in parallel, voltage is the same across parallel resistors. So here's basically a summary of what I just mentioned, okay, for current. And here's a summary of what I mentioned for voltage. So how we could represent this mathematically for parallel is the voltage across the battery, 9 volts, is equal to V1, which is equal to V2. They're all equal to 9. For the series circuit, the voltage across the battery, which is 9 volts, is equal to this voltage plus that voltage. But what about when I have a circuit that looks mixed like that? And when I say mixed, what I mean is I have parallel resistors over here. So the 8 ohms and the 8 ohms are in parallel. But we also have another 8 ohms over here that's in series. So how it works is as follows. The total current will flow through this part of the circuit. So A1 will read total current. The total current will flow through the resistor in series. Then when I see a split in the circuit over here, we know that the current will split. Some of the current will go through the top branch and the rest of the current will go through the bottom branch. And then they join again over here, and then the total current will flow through this part. Of course, this will only happen when the switch is closed, so just bear that in mind. So that is what happens with current. And I hope that you can be aware of the fact that, so A1 will read total current. It'll read total current. A2 will read a split current. A3 will read a split current. But what this means is if I had to take this current, the current reading on A2, and the current reading on A3, and I had to add them together, it would give me the total current. So basically, the reading on A1 is equal to A2 plus A3. So the current, the total current, is equal to the current in the top branch, so the current in the green branch, let's say, plus the current in the blue branch. I hope that makes sense. So current splits as soon as we have resistors that are connected in parallel. For the voltage, what happens is quite interesting. And what happens is the following. You can see that we have V1 over here. So V1 measures the total voltage or total potential difference or terminal potential difference, like we like to call it. So V1 basically reads the total voltage or potential difference. Now remember, voltage splits in series. Now what that means is that you see we have this resistor over here in series, and then we have what we call the parallel connection. Now I need you to understand that let's pretend, I'm just making up numbers over here. Well, I see here V1 is 24 volts. We can probably work out the actual amounts here. I'm not bothered by actual amounts. I'm just going to use make-believe amounts just to illustrate this concept. So say V1 reads 24 volts. Then if V2 has to get, let's pretend it is 10 volts. That means that the parallel combination will get the rest. So it will get 14 volts. I hope that makes sense because the total voltage, V1, is split between V2 and V3. So V2 is 10 volts, V3 is 14. 14 plus 10 gets you 24. Remember, I just made up these amounts. And now you might be saying, okay, I'm not really sure if I understand, ma'am, because these are in parallel. So what does that mean? Doesn't that mean that they get the same voltage? So wouldn't it be 7 and 7? No. Remember, how I want you to think of it is as follows. Think of it as this 8 ohm is connected in series almost with this parallel connection. Okay, so the green part of the circuit is connected in series with the blue part of the circuit. And we know that voltage splits in series. So this part of the circuit gets 10 volts. This part of the circuit, which is the parallel part, gets 14 volts. And what do we know about voltage in parallel? If we go back to our summary that I showed you over here, voltage is the same in parallel. So all that means is that if the voltage across the parallel connection is 14 volts, it means that the voltage across this 8 ohm resistor is 14 volts, and the voltage across this 8 ohm resistor is 14 volts. Okay, so 14 all over here plus 10 gives me the 24. And understanding that is actually really, really important for answering circuit calculations. Now, let's jump into using some of the formulae. Now, what I've basically done is I've copied and pasted important definitions that you may see in your textbook, in your exam guidelines and such. So we've got EMF, which is going to come into play in grade 11 and 12 more, but I want us to focus on all of these as being definitions for voltage, potential difference. Okay, and I want you to see the following. I showed you this formula earlier in the video, but look at how it connects to our definition. The potential difference across the ends of a conductor is the energy transferred. And remember, we said energy transferred is the same thing as work done. Okay, so energy and work is the same thing. So it's the energy transferred per unit electric charge flowing through it. Now, if you take a look at that in words, so the definition, and you look at my formula, they match. So potential difference is V. There's V. Potential difference is equal to energy transferred. Remember, W is the same thing as energy transferred. It's work done or energy transferred. So it's equal to the energy transferred per, when you see per, I want you to think of divide, per unit electric charge. And Q we know is charge. So again, look at the formula, look at the words, they match. So potential difference is equal to the energy transferred or the work done per, which means divide, unit electric charge. And it matches with our formula. So this is a very basic example of how you can get asked to use this formula. They say 2 coulombs of charge. So Q is equal to 2 coulombs. Remember coulombs, it must be in coulombs, not nano coulombs or micro coulombs, but it is in coulombs. Transfers 6 joules of energy. Remember, energy and work is the same thing. So work or energy, doesn't matter, is equal to 6 joules. What is the potential difference across the resistor? So we're looking for V. So we're looking for V, we've got Q, we've got E or W. So we use the following formula. We're looking for potential difference. The energy transferred or work done is 6 joules. And Q is the charge, it's 2 coulombs. So that means that the voltage or the potential difference is 3 volts. Another thing that I just want to show you about this formula, and they ask this sometimes in multiple choice, is we know that the unit for V, for potential difference, or for voltage is volts, right? Volts or V. An alternative unit, however, is as follows. What do we measure work in or energy? It's measured in joules. Per, this is a per line over here, it means divide. What's the unit for Q? Charge. We got joules divided by charge. Joules divided by charge. If you take charge to the top of the fraction, remember this has got an exponent of 1. If we bring that to the top, it's joules per coulomb. So volts, the unit volts, is the same as the unit joules per coulomb. So the flow of charge is current. We know current flows through a circuit. As soon as the switch is closed, current flows. And here's a little bit of a summary slide for current. So there's the definition. Current is defined as the rate of flow of charge. And something that I need you to know for physics in general and chemistry is that when you see rate, when you see the word rate, I want you to think of dividing by time. Dividing by time. Current is defined as the rate of flow of charge. So it's charge divided by time. That is current. And that's where this formula comes from. We know that the unit for current is amperes. So for example, 3 amperes. However, if you take a look at the formula, so current, let's do it on this slide quickly. Current is the rate of flow of charge. So it's charge divided by time. What is my unit for charge? Coulombs. What is my unit for time? Seconds. So it could also be represented like that, which is a very rare way to represent the unit. we represent it as amperes. But just be aware that they can ask you questions like that. So a type of question that you can get asked to use this formula would look like this. Calculate the current, so we're looking for I, that passes through a lamp. So a lamp is like my resistor. If 30 C, 30 coulombs, okay, that is my charge, 30 coulombs. So charge is 30 coulombs, current is what I'm looking for, and 5 seconds is my time. My change in time is 5 seconds. So the formula that I use is current is equal to charge divided by time, rate of flow of charge, 30 divided by 5, which is 6 amperes. A current of 0.45 amperes, so they're giving me I, flows through a light bulb for 1 hour. This is obviously time, but time is given in hours here. It must be given in seconds. How do we convert hours to seconds? I hope you know that you need to go from hours to minutes, which is times 60, and then minutes to seconds, which is times 60 again. So to go from hours to seconds, you times by 3,600. Okay, they want charge. So once again, you write your formula, you substitute in your value. So current is 0.45, that was given. Time is 3,600 because it was 1 times 60 times 60, or 1 times 3,600. That's how I got it from hours to seconds. And then you say 0.45 times 3,600, and there's my answer with my unit. So I'm going to say the total current in this circuit is 4.5 amperes, which means that 4.5, the total current will flow through here. As soon as we get to a split in the circuit, the current will split. Now, one thing that I do want to ask you is, remember, resistance is the opposition to the flow of current. And I hope you understand that that means if you have a high resistance, it's difficult for current to flow. So think about high resistance, difficult for you to get through. High resistance. Okay, so if I have two resistors, I have two resistors connected in parallel, a 6 ohm and a 6 ohm here and a 3 ohm over here. The 6 ohm has a bigger resistance. I'm going to write here bigger resistance. And what that means is it's more difficult to flow through this resistor. So remember, the total current will flow where you see blue, then the current will split. Some of the current will go through the 3 ohm, the rest of the current will go through the 6 ohm. They split, but the split is not equal. The reason they don't split evenly is because the resistors are different. Remember, 6 ohms has a bigger resistance, which means it's more difficult for current to flow. So what that means is because it's more difficult for current to flow through the 6 ohms, there will be less current traveling through the 6 ohm resistor. For the 3 ohm resistor, it's a smaller resistance, which means more current. I hope that makes sense. If you have a smaller resistance, so you're not really resisting, it's easy to flow. If you are current, imagine you're a current, you see 3, you're like, oh, that's not bad. 3 ohms, easy to flow through there. More current will go through the yellow branch. When the current sees a 6 ohms, they think, oh goodness, that's a very big resistance. It's very difficult to flow through the 6 ohm because it's bigger. So I'm going to avoid going through there. So less current will go through there. Okay. And I want you to also realize that this relationship is true because the voltage across them are the same. So remember we said the voltage across the battery is 9 volts, which means the voltage across the 3 ohms is 9 volts and the voltage across the 6 ohms is 9 volts. So what that means is the voltage is the same voltage, constant voltage. And because that's the case, if I have a big resistance, I'm going to have a small current. So just remember that the relationship between current and resistance is called inversely proportional, okay? And inversely proportional relationships, that is true. So current and resistance are inversely proportional. If voltage is constant, which it is because they're in parallel in this case, that means that if you have a big resistance, you have a small current. if you have a small resistance, you have a big current. And that is one thing that you absolutely need to know in grade 10. We go into this in more detail in grade 11. You can look at these slides so long if you are interested. So there's a slide, and I do mention that it is more grade 11 work, but I do want you to understand this concept. If you're in grade 10, you do need to understand that. And based off of that concept, I'm going to show you how we split currents when resistors are in parallel. So I actually want to start off with a basic example, which is one that I showed you already earlier in this video, and it looks like this. Remember, it was this example. Okay, so I am going to make up values for this just to make it a bit easier. Let's pretend that the total current flowing through the circuit is 4 amperes. And remember what that means is total current, if that's 4 amperes, it will flow everywhere where I'm highlighting it in purple or pinkish color. So 4 amperes will flow through all of that. As soon as it reaches this point, it's going to split. That means some of the current will go through the top branch. The rest of the current will go through the bottom branch, this one over here. Right, now, how does the current split? In this case, it is super, super easy. Because the yellow branch, do you see the yellow branch? The top branch has a resistance of 8 ohms. See, it just has that resistor, 8 ohms. And the green branch has a resistor of 8 ohms. It means that the resistances is the same. Because the resistances is the same, the current split will be the same, which means that the 4 amperes will split equally. What that means is 2 amperes of current will go through the yellow branch and 2 amperes of current will go through the green branch. 2 plus 2 is 4. Easy stuff. So the only reason that the current splits equally is because the resistance of the top branch is equal to the resistance of the bottom branch. And that is exactly what I wrote here for you. So you can take that down as a note if that helps you remember it. However, in this example over here, I hope that you can see that the two resistors in parallel, so they're not the same. What I've shown you on the screen over here, I hope this doesn't confuse anyone, is a snapshot of a circuit. So imagine it's like a little piece of a circuit like this. So I've basically just chopped off the piece of the circuit. So the total current is 6 amperes and it flows through the circuit like that. So 6 amperes is the total current and the total current continues there. And once it reaches here, the current splits. So it's just basically what I've done is I've taken a snapshot of a circuit, the parallel resistors. That's all I've done, so don't get confused. So total current is 6 amperes. It flows and then it stops. Some of the current will flow through the top branch. Some of the current will flow through the bottom branch, but it's not going to be 3 amperes and 3 amperes. I know 3 plus 3 is 6, but are these resistors the same? No, this is 5 ohms and that's 10 ohms. So you should know from what we've discussed, which resistor should get more current. Remember, the smaller the resistance, the bigger the current. So if R is very small, current is going to be big. So because 5 ohms is smaller than 10 ohms, 5 ohms will get more current. Okay, small resistance, big current. And what do you notice about the ratio of these resistances? It's a 1:2 ratio. I'll show you that in a second, but what I mean is this resistor is double the size of R1, which means that R1 should get double the current of R2. Okay? Because the resistance is half, the current should be double. They do the opposite. Remember, they're inversely proportional. I'm going to show you an easy way to do this, even if it is a little bit confusing. Doing this method will always work. So how we split current is as follows. We've got R1, R2. I want you to write down those resistors as a ratio. R1, R2. Then what I want you to do is I want you to write down the ratio of resistance. So R1 is 5 ohms. R2 is 10 ohms. I want you to simplify that ratio. So 5 goes into itself once, 5 goes into 10 twice. 5 to 10 is the same as 1 to 2. Divide both sides of the ratio by 5. This, what we've just written down, this is the ratio of resistance. Now, what did we just learn about resistance and current? They do opposite things. So the smaller the resistance, the bigger the current. So what I want you to do, and you will always do this when you are splitting currents, is you take the ratio of resistances and you flip it. So 1 to 2, you must write 2 to 1. That is what I now call the ratio of currents. If that's confusing why we do it, just keep reminding yourself of the relationship. Small resistor, R1 is small, so 1 is smaller than 2. Big current, 2 is bigger than 1. Okay, so just flip the ratio. So you write the ratio of resistances, 5 to 10, simplify it and flip it. Now what we're going to do is something that we did in grade 9 maths and grade 8 maths, where we split something into a ratio. So you may have learned splitting into a ratio differently in different ways, but what you do is you add the parts of the ratio together. So 2 plus 1 is 3. 2 plus 1 is 3. And what we now do is we say, okay, if I want to work out the current going through R1, so I'm going to write that at the bottom here, current in R1. What I do is I take the part of the ratio that corresponds to R1. So you follow R1 all the way down to the bottom, it's 2. So you go 2 over 3. Why over 3? Because the total parts of the ratio is 3. So 2 corresponds to R1, and we're looking for the current in R1. 2 over 3, because the total parts is 3, times by the total current, which is 6 amperes. I gave it to you over there. So basically what I'm saying is the R1, the 5 ohm resistor, R1, gets 2/3 of the total current. And 2/3 of the total current is 4 amperes. Okay? We can do the same thing, but for the current through R2. So what you do is, so that was current through R1. Should actually use a different color here. So let's use current through R1 as yellow. Okay, current through R1 is yellow. You follow R1 all the way to the bottom, 2. So current through R1 is 2 over 3. It's always over the total parts times the total current. So you always times the total current. Let's do it for R2. Let's see if it makes sense. So we take R2. Remember, R2 will get the rest of the current. You follow it all the way down to the bottom. It's 1. So we go 1 over 3 times the total current times 6. And that gets you 2 amperes. 1 over 3 times 6. So this is 2 over 3 times 6. This is 1 over 3 times 6. So in both cases, you multiply by total current. In both cases, you're dividing by the total parts of the ratio. For R1, you use 2. For R2, you use 1. And it makes sense. Think about it carefully. So the total current is 6 amperes. R1 gets 4 amperes. R2 gets 2 amperes. And we did say that the smaller resistor will get the bigger current. The bigger resistor gets the smaller current. We also said R1 is half the size of R2. 5 is half the size of 10. And because R1 is half the size in resistance, it gets double the current. 4 amperes is double 2 amperes. I really, really hope that that makes sense. I do suggest that you practice this. I have more videos on this. Check out the links in the description box below. But this is a summary of what we've basically learned. I hope that this has been helpful in the summary of electricity for grade 10. Please check out the links in the description box below. Remember to subscribe for more videos like this. I do physics, chemistry, and math. And I'll see you in another video very soon. Bye, everybody.